Okay, so what we will do is in these few lectures we'll talk about Kerr geometry. I will expect the audience to know some level of general relativity, perhaps at the undergraduate level, maybe an advanced undergraduate level course. And so you've had a little bit of different general relativity, but you haven't seen Kerr geometry in particular. So this would be valuable information. On the other hand, you may be a practicing astrophysicist and you need details of Kerr geometry. You may be a geometer who studied a year of differential geometry, but you haven't seen any applications to physics. And this would be an easy way to enter into black holes. It's the quintessential examples. It has all the eccentricities and good features that a black hole should have. It's a celebrated solution. Again, I'll keep the prerequisites to minimum, so we'll develop all the knowledge as we go along. And if I use any unusual notation, or perhaps I should say different notation from an introductory first semester GR course, I will clarify. Sometimes I'll use a more compact notation that mathematicians use. Very often I'll write it out explicitly, as you might find in a physics textbook. So perhaps let me begin with a recall. In Minkowski spacetime, the metric, or should I say the line element, is typically given by dt squared plus dx squared plus dy squared plus dz squared. This is in Cartesian coordinates. We won't spend too much time here, but if you notice the time coordinate, so, and I'm using coordinates t, x, y, z. Okay, this is negative, and the rest of the coefficients are positive. And very quickly, if I were a geometer, I might write this as a metric, and this would be replaced with dt tensor product dt, and so on and so forth. But very often this is more compact and it's easy to work with, so I'll write this again, keeping sort of the tone of an introductory undergraduate course. Well, we're not wed to any coordinate systems. That is sort of the mantra of relativity. So we should be able to freely move. And if I were to use, in particular, if I were to use a spherical coordinate system, the same line element will have the form and this is the line element for a sphere, and explicitly it is d theta squared plus sine squared theta d phi squared. Okay, so this is flat space-time in spherical coordinates. Now all of a sudden, and this you almost invariably have seen if you have taken an introductory course in general relativity, the Schwarzschild metric. And you can compare and see what happens, so you get a sense of how these metrics evolve. So it has to be minus negative in some sense. And this is partially to set notation. So it is negative with a correction, and it's a very important correction. And it too is spherically symmetric. Okay, this describes a spherically symmetric, static black hole. Static in the sense there's no time dependence, and time is on one side and space is on the other side. You know the eccentricities and all the features of the Schwarzschild metric. I write this just to make a comparison of what the main topic of our lectures would focus on, Kerr geometry. Notice in all of these metrics I have set C equals G equals 1, and I'll continue to do so. Very, very often it's easy to resurrect these things as needed, but we'll do it as needed. So let me write, and so you can see the deviation here, a Kerr metric in Boyer and it is somewhat of a spherical coordinate system. The expressions will be slightly more complicated. It has its difficulties, but then again, it's not just impossibly complicated either. So, because they're long, I will separate them out by simply writing it this way. And then later on, I'll tell you what these guys are. And then there is a 2gt phi dt d phi plus grr dr squared g theta theta d theta squared plus g phi phi d phi squared. Really, I haven't told you anything. I've just written something very, very general. But few expectations and perhaps clarification of notation. We would expect this, at least where time is time-like, this to be negative, and you'll see that feature. The second thing I'd like to clarify is this notation that physicists use that requires a little explanation. And you might say, why did I put this 2gt phi? The reason is, when written out as a metric, this would expand to gt phi dt tensor product d phi plus g phi t d phi tensor product dt. And the metric is symmetric. So gt phi and g phi t are the same, and hence the 2, and this is collapsed into just writing it as a line element. Okay, again, I have said nothing because I haven't told you what these coefficients are. Let me do so right away. And to avoid making mistakes, let me consult my notes. The curve in this coordinate system, the metric is defined in terms of few standard symbols. They depend on the various references that you use. The ones that I have gone through is the book by Chandrasekhar on the mathematical theory of black holes, and also Kerr, the geometry of Kerr black holes, or something to that effect, by Barrett O'Neill. That is an excellent book. It's a good book in modern differential geometric notation. Say your geometry is weak, this would be a very good book to read and to get the flavor, because the content and the presentation is not difficult, but the notation is new. You get a very good understanding of both geometry and every possible detail you would want of Kerr geometry in particular. So let me define a few functions. Rho squared delta and perhaps sigma squared, and that is r squared plus a squared delta a squared sine squared theta. So let me, before I write down the actual coefficients, let me point out this feature. All of you should know that this m stands for the mass of the space-time, mass of the black hole, as you might want to call it. It's a constant. This should be familiar to you from a standard introductory course. So if you notice, as I'm describing some of the variables, there are two constants. There is mass, or a symbol m. We have to justify that it's in fact possibly the mass, and another constant a. This will turn out to be the angular momentum of the space-time, or perhaps a black hole, per unit mass. Okay? So what are the metric coefficients? Well, GTT. It better have a minus dominating in the far regions, meaning when r is very large, and indeed that's the case. I have GT phi minus 2 mr a sine squared theta over rho squared GRR, and you can see what's, so this is a very new feature, right? So I've written it here just to expand notation, but this cross term is a new feature, and indeed is responsible for many of the effects we'll see in Kerr geometry. You will see that here minus 1 dominates. This is r over r squared, and GRR, if you look at GRR over here, well, at least in the Minkowski metric, when this is 0, this is just 1 in terms of r, and so you will find rho squared over delta, meaning factors of r. This is r squared. Delta is also r squared. That's what I mean. Okay, and g theta is rho squared. And finally, g phi phi. And if anything looks complicated, perhaps it's this uppercase sigma, where this is sigma. Again, in terms of notation, I have seen sometimes this rho written as sigma, but this is our choice, and we're going to stick with that. Any confusion so far? Is everything clear? Okay, we haven't done anything. We've just sort of stated the metric. I should also point out that this begins with just stating the metric. No discussion yet on how this metric comes about. And perhaps depending on how my lectures sort of go, we may get into that. We may motivate it slightly. But nonetheless, this is just a metric. This is also very much like Minkowski and Schwarzschild, Ricci flat. Meaning the right-hand side of the Einstein equation, T mu nu, is 0. So this along with these coefficients is a solution to R mu nu equal to 0. Okay, let's slowly get into it. As you look at the metric, you'll immediately see, just like over here, see when r equals 2m, this is somewhat unpleasant to look at. For one thing, the dt squared, the coefficient goes to 0. Well, that's bad enough, but this goes to 1, this becomes 1 over 0. So that's a telltale sign that something in the Schwarzschild geometry happens at r equals 2m. And all of you know that's where the event horizon is located. So let's look at Kerr geometry and see what are the potential sources of things going to 0, or rather things going to infinity. This is definitely going to be a problem. Delta equals 0 GRR goes to rho squared over 0 in the limit. And it's not just GRR, it's G phi, GT phi, and portions of GTT. So this, oh, no. Right, delta is just for GRR. But I really pointed out the next problem we might have is rho squared going to 0. I need some place to write new material, so we'll have to always expand with the old. So we will discuss these two case by case. Rho squared equals 0 and delta equals 0. Okay, this is very generic. It really doesn't help us much, so I'm going to get rid of this as well. Okay, now rho squared equals 0. If you look at this row, it's r squared plus a squared cosine squared theta equals 0. They're all positive terms, so this can happen when r equals 0 and, well, cosine theta is 0 or theta equal to pi over 2 simultaneously. That's an odd feature. R equals 0, yeah, it's a spherical coordinate singularity. That seems reasonable. But r equals 0 is not a problem, except in the equatorial plane, if you will, when theta equals pi over 2. That is an odd feature we haven't really come across. To understand that, what I'm going to do is I'm going to look at what r equals 0 might look like. So I'm going to take a curve, a circle, if you will. Okay, and this parameterizes as alpha of s is equal to, well, it should be t, r, theta, and phi as a function of s. So I'll fix some time. T equals some constant. I'm going to fix some angle. Now, eventually, I'll have to let that angle go to pi over 2. Oops, let me do this. R. And let me leave a little space. I'm going to fix an angle that I'll eventually let go to pi over 2. I've left a little space here. And phi of s, that's the only thing that changes as we go around this curve. Okay, just a ring about the z-axis, if you will. By z-axis, I mean theta equals 0. Really, we haven't mentioned any sort of a Cartesian coordinate system here. Now, this is peculiar that I can do this, and as I'm doing this, I'm mindful that my diagram already does not begin to make sense. This is going to be the problem, so I'm going to let this equal to 0. It's odd that I want to draw that like this because it says r equals 0. But that's okay. Bear with me. Let's see what I'm headed towards. So the velocity of this curve, and this is some s. I can pick phi of s to be equal to s if you want. So then the length of this curve is nothing more than the velocity with respect to d alpha ds, the length of the velocity times this function. If phi of s is s, the limit s goes to, the integration limits is 0 to 2 pi. And so that is equal to 0 to 2 pi. This is only the phi component, and d phi ds is 1. So and mind you, r equals 0 and theta equals some theta 0. Again, on a very confusing diagram, I'm going to write theta 0. We're going to let theta 0 go to pi over 2. Remember, we'll have to tackle this delta. And so the length, it's not a very complicated integral, as you'll see. I'm going to take this expression for g phi phi and let r go to 0. And turns out it is a to the 4th minus a to the 4th sine squared theta over square root, so a squared cosine squared theta, and then there's sine squared theta ds. There's no s dependence anymore, and this is at some fixed angle. Well, this is just 1. Sorry, a. I bring out a squared, I get a. And so the integral is very... Now why should this be puzzling? Along this path, seemingly wrongly drawn, r is 0. And yet, it has a length of 2 pi a sine theta 0. As a matter of fact, as theta 0 goes to pi over 2, and we need pi over 2 simply because that's where the singularity is. What I get is the length of a ring, if you will, very classically speaking, is a circle of radius a. Something that is geometrically, topologically a circle of radius a. And so, in the limit, my diagram looks something like this. So this is my equatorial plane, if you will, and just an intuitive picture, it is not a measure, this is a ring of radius a. I'm hesitant to do this, but I'm going to still do it just so that you get an understanding of what's going on. And this is actually in the so xy plane. I could make it even a little more. Yeah, and this. It's a ring of radius a in the equatorial plane. So this, the singularity in the metric coefficient is famously called the ring singularity. Of Kerr geometry. Now the question is, as with Schwarzschild and in differential geometry, is this a feature of the coordinate system, or is there something more? Is it deeply something about the geometry or with the coordinate system? We'll have occasion to see that this has got to do with the geometry. This is a true singularity of the Kerr geometry, and it's a ring, and the radius of the ring depends on the parameter A. I had mentioned before, and we'll have to work a little hard to see that this is in fact the case, that A corresponds to the angular momentum of the space-time, if you will, angular momentum per unit mass. And so the angular momentum decides the size of the ring, if you will, on the XY plane. On the equatorial plane. More precisely, the submanifold you get when you fix time and when you set theta to be pi over 2. Okay? Again, what's most curious about it is the fact that on this ring of this length, the r coordinate is 0. In our Cartesian experience, in our spherical coordinate system experience, if r is 0, it doesn't really have any structure. But here it does have structure. Now here I'm only taking the limit because the space-time itself is not defined at that ring singularity. So I'm not setting it equal to 0, although these are continuous functions, and that's literally how you take the limit. Okay? And so now we have, so for now, let's hold our breath, knowing fully well that rho squared equals 0 is a ring singularity. It's suggested, at least for the moment, that's a true singularity. We'll find out this is the case. And now we'll have to tackle the delta equals 0 singularity. But before I do so, any questions? Let me write out some standard relations that'll come very handy as you do problems in Kerr geometry. I found this in the book by O'Neill. It just makes the conversation a whole lot easier. For lack of a better name, I'm just going to call it canonical relations in Kerr geometry. It's really a Boyer-Lindquist feature. It is not a coordinate independent, it's just an algebraic relationship. This is easily verified. If you're patient and you're slowly getting used to general relativity and Kerr geometry, you may actually want to verify this by hand, at least one of them, and check with O'Neill to make sure that I have copied it down correctly. I should clarify, this is on his, in his Kerr geometry book and not in the book on semi-Riemannian geometry. Both are excellent books, excellent references. Hands down, the best description of Petrov classification is in the Kerr geometry book. It's a quick read, very clear. Okay. If you look at the square root of the metric, of the determinant of the metric, it's going to be negative, so to take a square root, you have to put a negative sign. Turns out this is rho squared sine theta. And we don't want the metric to be degenerate, so we would want the determinant to, or the square root thereof, to be non-zero. And indeed, you find that theta equals 0 or pi. This is 0, and at the ring singularity, it's 0. So this, if you will, the polar axis, we will see explicitly by the construction of a coordinate system that this is a coordinate singularity. And this is a problem that we cannot get rid of. We just have to learn to live with it. And in fact, it has remarkable consequences. Yep. So now, the other problem. The expression for delta is minus 2mr plus a squared equals 0. Simple quadratic equation. If you solve for r, you get two values, which I'll denote by plus and minus. And you might as well get used to it. I will refer to r plus and r minus as horizon. Okay, the outer horizon and inner horizon. The meaning will be made very clear. But much like the event horizon of a short shield, there are two here, so it's r plus and r minus. Okay, and we would actually want two here for many reasons. So by and large, for the duration of these lectures, I would take m squared to be greater than a squared. And we'll also take a to be greater than 0. If a is not greater than 0, you simply swap the direction of phi, the direction of rotation, if you will. And so our case is this. Towards the end, perhaps, if we find it interesting enough, we might consider the limit as a approaches m. When a is greater than m, notice there are no real horizons. This is a complex number, which means they're not realized in nature, and the physics doesn't get to be very interesting. Perhaps it is academically interesting. You get what you call a naked singularity, where the ring singularity is not cloaked behind anything. But we might briefly discuss it, but by and large, we're going to focus on this. Okay? So we have the ring singularity and the two horizons. Let me just write that down so that as I call r plus and r minus as horizons, you know that's what I mean. R plus would be the outer horizon, the greater value. R minus would be the lower value. Okay. There is one other critical point or surface that is very interesting to Kerr geometry, and that is the infinite redshift surface. By calling it horizon and infinite redshift surface, we're already labeling them that it suggests something. Indeed, we have to show that our suggestions are correct. And we'll have to work a little hard for that. So this is located by the condition that GTT is 0. Now, why is that important? In the beginning, particularly looking at Minkowski metric, we talked about how the time component has to be negative. right? So this is if this does indeed occur, that's a point where the time component is 0, meaning it, and then beyond that you will see it becomes greater than 0. So the coordinate t stops behaving like time. So this is a telltale sign that coordinates don't mean much in relativity or geometry. Right? It's the metric that tells you the properties of these objects. So just because you see a symbol t, don't say, well, it's time coordinate, and you see a symbol phi, oh, it's your azimuthal angle. That doesn't have to be the case. It doesn't even have to be closed just because you have phi. If you're making it closed, it is for an entirely specific expectation. Very often, it is of the expectation that infinitely far away, for very large r, life looks like Minkowski. And that's the reason we topologically close phi. Just because you see symbols that you're familiar with in your Cartesian Minkowski world, you shouldn't attribute those qualities to differential geometry or general relativity. So this turns out to be -1 plus 2mr over rho squared equals 0. Rho squared is also r squared. Once again, this too is a quadratic equation, so you would get plus or minus. And I called it infinite, so might as well put infinite. I'm going to leave a little space, and you solve for r. Notice that, or recall rather, this one has r squared plus a squared cosine squared theta. And as a result, and because the surface, the location is theta dependent, that's the reason I left the space, the infinite redshift surface looks like so. So while I have, again, I have not attributed meaning to any of these quantities, just labeling them. We'll classify space-time, our space-time, and study it and bring these meanings very clearly. Let me draw a diagram so that you know what's going on. So you have two horizons. And it's part of a circle. I'm only going to, for just artistic reasons, I'm only going to draw 1/4 of it. You really have to complete it into a circle and then rotate it. Okay? So this is r plus, this is r minus, and then you get this, the infinite redshift surface. And if you look at this a little carefully, you'll see that this is what it looks like. So this would be r plus infinity theta and a minus. Okay, certainly not to scale, minus infinity theta, and the ring singularity. All of this has to be made sense, has to be understood. You have to see what they mean. It is very standard for the outward region, all of when r greater than r plus, to call that block 1. Block 2 would be between the horizon, r minus, between the two horizons, and block 3 would be r less than r minus. Okay, so outside of these curved white lines, they're in fact spheres, topological spheres, and so this the exterior region is block 1. Between the two horizons, you get block 2. And inside, you get block 3. And in the various blocks are the infinite redshift surfaces and also the ring singularity. Again, I've only drawn 1/4 of it. I need to complete the diagram. I just don't want to clutter my drawing, and also imagine this to be rotated in space. We will study these features one by one. Let me talk a little bit more before we end for the day. And yeah, so we can already talk about M, the symbol M. Recall from your GR course that GTT, if you expand in terms of R, it goes as, well, it should go as -1. But beyond that, the first level correction is -2 phi, where this is the gravitational potential. In the case, this is in general. So this is a fact, if you will, I have recalled from introductory GR course. Again, we're assuming so many things, that T is the time coordinate system, very far away, and then it's asymptotically flat, asymptotically Minkowski, if you will. And so in our case, -1 plus 2mr over rho squared. With a little algebra, you can see I can write this as, let me make sure the expression is correct, 2mr. Really, I want factors of r, and 1 plus a squared over r squared cosine squared theta -1. That is the exact. I mean, you just multiply it out. You'll find you'll find that this is in fact that. But let's approximate very far away for large values of r. For very large values of r, this is already a 1 over r term, and these things, this entire term can be ignored. So then GTT goes as -1 plus 2m r over r squared, or 2m over r. A direct comparison tells you that the gravitational potential is -2, let me leave a little space, I'll explain why, -2m over r. Again, you know from freshman physics, if I were to resurrect all the symbols C and G, turns out this is just 2gm over r. Indeed, it is the gravitational, there shouldn't be a 2. Yep, there's a 2 here, so that means, yeah. So this will tell you that you know from your classical mechanics course, that's the mass of a star, if you will. So this is one way, one quick, easy way, without using any sophisticated methods, to see that this space-time, the symbol m stands for mass. So we have gone far, we have explained the geometry, we have identified all the problems to be discussed, we have described, shown that m indeed stands for mass. At the moment, a is this parameter, suggested that it is the spin. Nonetheless, there's a ring singularity whose size depends on a. So I think it's a good place to stop now. Any questions?